Okay, so far we've been talking about a very simple model of coalescence where we assume that everything is randomly mating, randomly mixing, there's no population subdivision. But if we have a real population in some two-dimensional space, well, the probability that this individual and this individual have a common ancestor in the last generation is probably smaller than if two individuals are near each other, right? It depends on certain things, but real biological organisms, we expect to have more complex biology than just random mating. We're going to start now with the major way that this has been looked at before. In this model, we imagine there's some number of subpopulations. Here we have two, with some individuals here and some individuals here, and we imagine that every generation, each individual has a probability m. M's not great to get used, is it? Because we've used mutation for m. This is what's generally used, so we're going to go ahead and use it. So m is the probability that any individual here moves over there. Okay, and so this is a quite simplified model, of course, but it can be shown that more complex models have many similar features to this, and this makes the math a lot simpler, which is why we're going to start here and why the theoreticians who built this started here. Okay, so then if we have two individuals, we're going to again ask what the expected coalescent time is for two individuals sampled from this population. So if we sample two individuals, they're either going to be from different populations or they're going to be from the same population. And that's going to matter. So let's just start with one of them and then we can back out the other one. So let's start with individuals in different populations. Okay, and so now if we follow these individuals back generation by generation, and I think I'll go ahead and do this. So now we can do the same thing that we're doing, which is now we have a bunch of individuals in this subpopulation, and we have a bunch of individuals in this subpopulation. So if we're following two individuals that are in different subpopulations, and we're following them back in time, then if mutation is small, then most generations what happens is just this individual has a common ancestor in this population, and this individual has a common ancestor in this population, right? So then that's basically just what's going to happen. So the rare thing that's going to happen is when this individual's common ancestor actually is from the other population. Right, so that's a migration event, and the chance that the individual we are following here has a migration event is m. Okay, so basically now what we're waiting for is in our sample we're waiting for one of the individuals to have a migration event in their history. So the probability that this one, or the rate at which this one migrates is m, the rate at which this one migrates is m. And so the rate of migration is 2m.